Okay, so I want to talk about something that's kind of odd sounding, and that's the angular velocity of something that's not rotating. You think, well, how can it have angular velocity if it's not rotating? So let's consider, for example, that we've got an aircraft. And so we have an aircraft, it's got mass m, it's moving at some velocity v, and at some height h above the ground. Okay. And down here somewhere we have a farmer. Okay, so we got a farmer standing here, and I guess this is his cow, and he's got a pig and then a goat. Okay, all right. So, and then so anyway, farmer's down here, and I guess he might even have, a chicken. Okay. So anyway, he's standing here out in his field, and he sees the aircraft up here. Okay, so angular momentum is r cross p. Well, obviously there's momentum p right here. There's an r right there. Okay, and so there's going to be an angular velocity right there. Now, as the aircraft is moving along, then what's happening is that r keeps changing. Okay, well, yes, r keeps changing. P doesn't change, r keeps changing, but the angle is changing here too. So let's look at it. What's the magnitude of this? The magnitude of the angular velocity is going to be rp sine theta. Well, wait, we can do algebra here. That's going to be p r sine theta. What is r sine theta? R, this is theta, so that means this is theta. R sine theta is going to be h. Likewise, r sine theta is h. So that means the angular velocity is going to be basically just p times h, or in other words, just mvh. Okay, so it turns out the angular velocity in this case is constant. And you imagine it would be if the net torque is zero. And so the aircraft's moving at constant speed, and it's in a straight line, and you don't really think about it as not as having angular velocity, but yet it is obviously having an angular momentum here. Well, angular momentum is I omega. Now, I is mr squared omega. So how does that play into this? Well, the m stays constant, the r is changing. So when it's far away, r is big. When it's close to overhead, r is small. And so that means as this gets smaller, omega has to get bigger if L stays the same. L is a constant. So that means if you're standing out here, looking at an airplane go by, so you're standing out here looking at an airplane, the airplane, because R is big, then omega is small. Remember, angular momentum, I omega. So that's going to be mr squared omega. So if r is small, omega is small, but as the airplane gets closer to being overhead, it looks like it goes faster, and then it looks like it's slowing down again over here. You've noticed that. You've gone out, you've seen airplanes fly overhead, and so as you stand there watching them, it's not like the pilot looks out the window, sees you, and guns it to get past you quick. They're flying at constant speed, but it looks like it's going quicker when it's a little bit closer to you and more overhead than it does if it's far away. Same thing with a car driving past. You're standing alongside the road, and as the car is coming towards you, when R is very large, then it doesn't look like it's moving that fast, but the same car going the same speed looks like it's moving very quickly if R is small and it's passing you. And so this is an example of angular velocity, angular momentum for things moving in a straight line. Because as it's moving, as far as you are concerned, the angle is changing. And so that's why these angular terms still apply to something moving in a straight line.